Section 7 is about freefall. And freefall is just the idea of an object moving only under the force of gravity. There's nothing else touching it, there's nothing else acting on it. No air resistance, it's not sitting on a table, it's not hanging from a rope. The only force, the only push or pull acting on it is gravity. Now, one of the tricky things about free fall is the word fall. A lot of people think that in order for it to be in free fall, it should be moving downwards. But that's not the case. That's not what it means, which is counterintuitive. It could be going upwards. As long as the only push or pull acting on it is gravity, we can say it's in free fall. So let's imagine a ball, and let's say that's going to be pushed up by your hand, and then it'll launch out of your hand and travel upwards, reach the peak of its path, and then fall downwards, and then impact the ground. So here it's going to be being pushed up by your hand, so I can maybe imagine my hand is underneath it, pushing it upwards. But then right at this instant, how about we call that instant 1, 0, 1, 2, 3, 4. Right at instant 1, it leaves your hand. And then from 1 to 2, let's say that it's just kind of moving upwards on its own. Gravity will be slowing it down. And let's say that we can ignore air resistance. It's so small that we can ignore it. Ball moving up and slowing. Air resistance. Is ignored. And then from 2 to 3, let's say that the ball is moving down and speeding up, because gravity will speed the ball up as it falls. And let's say again that air resistance is so small that it could be ignored. Like, let's not imagine a feather where air resistance would obviously matter and that would cause the feather to float. Let's imagine a tiny ball bearing, something that's really dense. Ignore air resistance. And then let's say from 3 to 4, let's imagine the ball actually stopping while it's hitting the ground. My diagram's not perfect, but let's just go with it. Alright, so from 0 to 1, I would say that the ball is not in freefall because it's being pushed on by your hand. From 1 to 2, the ball is in freefall because there's no air resistance, we're ignoring it, and there's no other pushes or pulls acting on it. There's no hands pushing on it, after the launch, and there's no strings or anything else. So from 1 to 2, it's in freefall. And then from 2 to 3, it's still in freefall. because gravity is the only push or pull acting on it. And then from 3 to 4, during the hit, during the stop, it is not in free fall because it is touching the ground. The ground will be pushing on it. So it's free fall from just after launch to just before impact. And it's important to make these distinctions of just after launch and just before impact, because whenever the ball is in free fall, from time 1 to 2 to 3, it has a very specific acceleration, the free fall acceleration. So let's say A, and then maybe give it a little subscript of A free fall. The acceleration of free fall is 9.80 meters per second squared. And then I'm going to say downwards, because gravity is always working downwards. And remember that those kinematic equations could work during time intervals whenever the acceleration was constant. So we can use the kinematic equations to calculate some quantities for this ball, whether it be from time interval 1 to 2, or from 2 to 3, or from 1 to 3, because during this whole green arc here that I've drawn, the ball has the exact same acceleration. The kinematic equations work. We don't really want to use the kinematic equations here from 0 to 1. We don't know if it has a constant acceleration here, but it would not be the acceleration of free fall. And the same thing for 3 to 4. So let's introduce a little bit of an abbreviation here. G is going to be defined as positive 9.80 meters per second squared. So then the acceleration of free fall would be equal to G, but downwards. So I'm going to quick do an example problem, but I'm going to do it 2 different ways. One with a coordinate system counting upwards to be positive, and a different one with a coordinate system counting downwards to be positive. So let's say that we have a ball that is dropped, and then it'll drop, and then we'll let it fall for 2 seconds and then find its final speed. VF is equal to question mark. All right, so that's what we have. Let's find the final speed. So let's assign a coordinate system. And I'm going to happen to choose a coordinate system that's going to count as positive, the positive y direction to be upwards. You could choose your origin to be here or here. How about I put it to be here? Y is equal to 0. So we know that the ball was dropped, basically meaning that its initial velocity was 0. And let's just assume that air resistance can be ignored. So then the acceleration here is implied, and you have to figure that out. So what's the acceleration from just after it's dropped, just after it leaves your hand, during this whole time that it's going to be falling for 2 seconds? The acceleration in the y direction would be 9.80 meters per second squared, but downwards. But isn't downwards your negative in the negative direction? So we could say that would be equal to negative g, which could also be negative 9.80 meters per second squared. So then if I use this equation, A, and instead of it saying AX, I'll say AY, is going to be equal to the change of the velocity in the y direction divided by delta t. Now if I rearrange that, I can say that delta Vy is equal to AY times delta t, basically just multiplying delta t to both sides. Delta Vy is the final V minus the initial V. but the initial v, the initial velocity, was 0. So vyf is going to be equal to ay, negative 9.80 meters per second squared, times delta t, 2 seconds. So it'll be negative 19.6. And then one of these seconds in the denominator can cancel out with that one, so we get negative 19.6 meters per second. I'm going to round it to 1 sig fig because of this 2 here was not very precise. So I'm going to say 20 meters per second, but the negative meant downwards, right? Because positive was up, so negative means downwards. Now let's do this again, but let's say I had a different coordinate system. So again, we had the initial position here where it was just dropped. So it starts off with a velocity of 0, dropped for 2 seconds. vyf is unknown. Now let's have a coordinate system here where I'm going to say going downwards is going to be counting positive. So if this is my origin, then it'd be positive 1 meter, positive 2 meters, positive 3 meters. Here, our acceleration in the y direction will just be positive 9.8 meters per second squared, or positive g, because gravity works downwards. The acceleration of gravity is always downwards, and we called our downwards to be positive. So if I use the same equation that we had used before, bxf is equal to ax delta t, but this time I'm going to plug in a positive acceleration because that's how we decided we should align our coordinate system, which will be 9.80 meters per second squared times 2 seconds. So we get positive 19.6 meters per second, and a positive here means downwards. So if I round this to 1 sig fig again, 20 meters per second downwards. So we end up with the same answer, 20 meters per second downwards. But in the first case, the first student who did that, they ended up with a negative value to indicate that. And somebody else doing it this way would end up with a positive value to indicate that.